Okay, this is, I'm going to go over a few of the review problems that you were assigned, not all of them. You need to be sure you're using a colored pencil to check your work and make any corrections and make any necessary notes that you need. And then if you have additional questions, just ask. So we're going to start. I have not numbered these. You've done your review. If you've done what you're supposed to, you've written the problem down, so you should be able to follow along. If not, be sure you have your book open as always to follow along. So the first problem I'm going to start with is the square root of 49x squared y to the 10th. So to simplify this, we would normally make two radicals below it and we would write perfects and leftovers. But as I glance at this, I should recognize that 49 is a perfect square. X squared and y to the 10th are both even, which makes them perfect squares. So I don't need two radicals, just square root everything. So square root of 49 is 7. Square root of x squared is x. Square root of y to the 10th is y to the 5th. Now, just when the question asks, you need to put absolute value bars when needed. The time that you need absolute value bars is if you are doing an even root, as this one is, a square root, and it's possible for your answers to be negative. Because remember, when we have this symbol, this radical, we only want the principal root. And for an even root, that means positive. Since certainly x could be negative and y to the 5th could be negative, then your answer should have absolute value bars around those two. Now, that is only when the question asks, and it's not something to take a lot of stress over. If you forget, don't worry about it. Don't just stop doing the problem. You can still do the problem, okay? So from the rest of the questions on, we're going to assume the variables are positive and we're not going to worry about the absolute value bars to make things a little easier. So the next problem, we're going to do the square root of 32 x to the 9th y to the 5th. This time I should notice that 32 is not a perfect square and neither is or x to the 9th or y to the 5th, both odd roots or even root, and then they're odd powers. So I'm going to make my two radicals as we have done over and over and over again. In the first radical, I need to split 32 into products. I'm trying to multiply two things together that make 32, and then I want to find a perfect square. Well, if you write down all the factors of 32, you'll see that 32 can be made as 16 times 2. It can also be 4 times 8. 4 is a perfect square, but we are always looking for the largest. We want to get as much of the perfect parts out as we can, so we would want to use 16 times 2. We do the same thing with the exponents. Remember that with exponents, they work different. When you multiply with exponents, you add the exponents. So we are looking for a power that is the same number added to itself, which would mean it has to be even. The closest even exponent to x to the 9th would be x to the 8th, and that would give me an x left over. Combining those, x to the 8th times x, we would get our x to the 9th. And we've just simply split it. It's like taking stuff and separating it into two piles. The perfect in the first part, leftover in the other. And then the same thing was true about 16 times 2 is your 32. We're just splitting it. Y to the 5th, we do the same thing. We look for the even that is closest to 5. So that would be y to the 4th. And that would again leave us a leftover of a y. Now the reason we separated it is all the first parts can come out from under the radical. They're all perfect. We can actually square root them. So the square root of 16 would be 4. The square root of x to the 8th would be x to the 4th. It is the number that I add to itself to get 8. Another way to look at it, with exponents only, not regular numbers, but with exponents, 8 divided by 2 would give me that 4. And so y to the fourth, if I square root it, would be y squared. And then as always, the leftovers just get tagged on to the end. And so this is our answer for this problem. Okay, on the next problem. It looks a little more complicated, but all we have to do is first combine everything and then split it into perfects and non-perfects. Things that are outside of the radical stay outside, inside multiplies together with other things on the inside. All of the operations we have here are multiplication. So 2 times 5 is 10. That's outside. We're done with the outside numbers for now. Now make a third root and a bigger radical and just start multiplying the stuff that's underneath the radical. So we have 2 times 6, which is 12. We have x squared times x to the fourth. And remember, we add exponents, so that would be x to the sixth. Y times y to the fourth would be y to the fifth. Now on the next step, we're going to split into perfects and leftovers. The 10 is already perfect, not under a radical. It's all been dealt with, so it just stays out there all by itself. Then make your two radicals perfects and leftovers, and then just start splitting everything. So we have each thing we look at and split it just like we did on the example above. So we look at the 12. You should be able to quickly see that we can split 12 as 4 times 3, and then x to the sixth. Well, oh, and I'm sorry, that's not going to work for 12. This is a third root. I need to pay attention to what I'm doing. So we're looking for a perfect cubes, not perfect squares. So this may have happened to you also. This is why we use pencil. All right, so we are looking for a perfect cube that goes into 12. Well, there aren't any. The smallest perfect cube less than 12 is 8, and 8 doesn't go into 12. That makes the entire 12 a leftover. So the whole thing goes in the leftovers. Now we need to look at the exponents. So this time I want to know what number would I add to itself 3 times to get 6. So that would be 2 plus 2 plus 2. So x squared is what you would end up with after we perfect or do that. So x to the sixth is a perfect. Then for y to the fifth, well, we have to add a number to itself 3 times and still stay under 5. The only thing we can do there is add 1 plus 1 plus 1, which gives us y cubed. If you remember, we practiced this, and whatever the root is, the exponents that are perfect will be multiples of that number. So the closest multiple of 3 to 5 is y cubed. That leaves us y squared left over. And now we just need to simplify each of those parts. So we're going to have the 10 still staying outside. And then you're going to third root x to the sixth, which is x squared. Third root of y cubed is y. And then you'll have times your leftovers, 12y squared. So really the only thing we have left to do here is just not write it with a dot. If there had been a number after we had done our perfects, then we would have multiplied that number by 10. But in this case, we didn't have one. So this is our answer to the problem. And notice we want to leave a little bit of space between the y and the third root symbol there. We left a little space there on purpose because we don't want it to look like y cubed. Okay, so now let's go to the other examples on the right hand side here. So next example is the third root of negative 64 y to the ninth. Well, the third root of negative 64 is a perfect, and y to the ninth, as we just talked about, is a multiple of 3, so that's also perfect. So third root of negative 64 is just going to be negative 4. Third root of y to the ninth is going to be y cubed. We just divide 9 divided by 3 to get the cubed. That is, again, only true for exponents, so be careful. Okay, next example. Square root of 10 times square root of 40. So again, multiplying, so we simply multiply both of those things together underneath one radical. Then we split into perfects and leftovers because 400 is not a perfect square. Or we don't know if it's a perfect square. Let's put it that way. It's bigger than our list. So first thing I would do is take your calculator and try square root of 400. Well, we're actually going to find out it is a perfect square, but I think on our list we only went up to 18 squared, so we might not have noticed that. So no big deal. If I wrote two radicals, I just only need the one. So square root of 400 is 20, and I'm finished. So don't stress over, oh, I don't know if I write two radicals or if I shouldn't write two radicals or does it work out, because just like that one, we went ahead and wrote two radicals, found out in fact 400 was a perfect square, no big deal. There's nothing in the leftovers, not a problem. Okay, next example. These are being again multiplied. They're under a radical, so they can get multiplied together under one radical, just combined together. So just deal with the things that are alike. So your number times your number, so 5 times 45, which is 225. Then do your exponents. Your x's first, so we have x to the 4th and x cubed, which is x to the 7th. We add exponents. Y cubed times y is y to the 4th. Then we're definitely going to have at least one thing that's not perfect, and that's the x to the 7th. So I'm going to go ahead and make my two radicals, perfects and leftovers. And then I'm going to split anything. Well, 225 should be on your perfect sheet. If you don't remember if it is or you don't have your perfect sheet, you just take a calculator, square root of 225 comes out exact, so it's a perfect. X to the 7th is not all perfect. We have the even power that is perfect, so that's x to the 6th. That gives me a leftover of just a single x. And then we have y to the 4th is even, so it will be perfect. And then we do, as we did on the other examples, the square roots in the perfects all come out even. So square root of 225 is 15. Square root of x to the 6th is x cubed. Square root of y to the 4th is y squared, and then tag on your leftovers. All right, so let's go to the next part of examples here. We're starting with, we'll do some dividing and then some adding and multiplying. So let's start with the division problem. All right, so kind of like multiplication, I mean, it's very much like multiplication. They're each under their own radical, so we simply make one radical with the entire division problem underneath. Then you're going to reduce anything in that side, that radical, to get the problem simpler and then see what we need to do with it. So 56 over 7 is just like elementary school, just divide the fraction. You find that it equals 8. Y to the 5th over y, remember if you need to, you can put a 1 there, so you remember it's y to the 1st. For division, either we subtract the exponents and we do 5 minus 1 to get 4, or we think there's 5 in the top, 1 in the bottom, so one of these cancels with one of those, and that leaves me 4 in the top. So then rewrite this so we clean it up a little bit, and all we have left is 8 y to the 4th under the radical. Now make your two radicals, your perfects and your leftovers. If we're remembering that we have cube roots here, so we look for the cube root of 8, and it is indeed perfect, so it can go there. Y to the 4th, again, for exponents, you're looking for a multiple of 3, so that's y cubed. You have a leftover of 1y, so your answer will be third root of 8 is 2. third root of y cubed is y, and then your leftover third root of y. And that's it. Let's go ahead and do this problem over on the right first, and then we'll do the one on the bottom. So in the problem over here on the right, we have adding. And we've talked about that adding complicates things a little bit in sometimes as we get into a little bit more advanced things. So when we add, we can only add together things that are alike. Well, 27, 75, and 12 are not alike. So these are not like terms as far as we can tell at the moment. So what we do, we need to go over to the side to find a scratch area, and then we're going to simplify each one of those radicals, put them back into the problem, then answer it. So we have the square root of 27. So again, you're going to do perfects and leftovers. Be sure that you are writing those words out if you're still having trouble until it sinks in. Okay, so for 27, we're looking at perfect squares. So that could be written as 9 times 3. 9 is a perfect square. So that gives us 3, and then we have the square root of 3 left. So we can come back over to this problem, and instead of the square root of 27, we'll write 3 square root of 3. Then let's do the square root of 75. So we do the same thing. We put perfect squares, leftovers. Well, 75 is 25 times 3. Square root of 25 is 5. Square root of 3 left. So plus 5 square root of 3. Then come over here and do the square root of 12. Square root of 4 times the square root of 3. That's 2 square root of 3. I went through that pretty quickly. Pause it, go back, look at it again, think about it if that didn't make sense. Now I can see that all of the radicals are square root of 3. So now they are like terms. The number in front is just how many we have. So we have 3 plus 5 minus 2 of these square roots of 3. Now you're not going to write this normally, but this is what we're doing. We need to add those numbers together to find out how many square roots of 3. So of course that's 8 minus 2, which is 6. So we have 6 square root of 3. Okay, let's go down to this problem at the bottom that has multiplication. Well, you're going to multiply this just like you think you would. You're going to distribute or use FOIL. It depends on how you like to say that. So you just need to be sure that everything in the first polynomial gets multiplied by everything in the second one. And the way we can keep track of it, we can use the acronym FOIL, or you can just keep track of it by distributing. It doesn't really matter, whatever makes most sense to you. So I'm just going to start with the 5, and I'm going to multiply first 5 times 2, which is 10. Then I'm going to take the 5 and multiply it by negative square root of 3. Well, the 5 is not under a radical, so it stays outside. Square root of 3 stays just like it is. There was a negative in front, so it's minus. Now I'm going to simply multiply the square root of 3 over here times 2. So again, 2 is outside, square root of 3 is inside, so that's 2 square root of 3. Then take the square root of 3 times a minus square root of 3, and that will be minus. Now you can multiply under the radical because they're both under the radical, so that's the square root of 9. Some of you will recognize right off the bat that that was just a 3, and you can just write 3 there. Now we need to go through and just simplify what we have here. So we see right here in the middle that we have like terms. At the moment, we don't have anything to go with the 10, so we'll just write the 10. We have negative 5 square roots of 3 plus 2 square roots of 3, so that's negative 3 square root of 3 minus, and now again, instead of the square root of 9, that's 3, because that's a perfect square. Now I have one more step. Now I do have two numbers that are alike, just the 10 and the -3. There's no radicals with them. They're just regular numbers. 10 minus 3 is 7, and then minus 3 squared of 3. We cannot do anything with that. Okay, it's not a like term. All right. Now, next few examples have to do with rational exponents. A lot of this was just rewriting them, just putting them in radical form. And when we have numbers, a lot of times that's what we're going to do. The instructions for the first three problems there on the top were all to change them to radicals. So we just need to remember that we have power over root. So that makes this fifth root of 3 to the first, which we don't write usually to the first, so it's just the fifth root of 3, and that's it. Next problem, again, power over root. So 3 is the root, it's an x, and it's being raised to the second. The last problem over here, we need to remember what a negative exponent means. A negative exponent means you should write 1 over 2 to the positive 3/4. Then we can change it to a radical at that point. We have to get rid of the negative. It doesn't really make any sense to do a negative power, so we change it. So here you still just have 1 over, and instead of 2 to the 3/4, we'll do 4th root of 2 cubed. But in this case, since it's a number inside, we can actually write 8, because 2 cubed is 8, where we couldn't do that with the x when it was inside. Okay, so just remember, negative exponents mean 1 over that number to the positive, or if the negative exponent was in the bottom, you can move it to the top and make it a positive exponent. That has nothing in the world to do with regular numbers being positive or negative. And if a regular number is negative, it does not mean 1 over. It has never meant that, and we haven't changed that. Exponents work different. Okay, now let's go to this one here with the number 243 to the 4/5. Same thing, fifth root of 243 to the 4th. Well, we could write the 4th inside and do the 4th power first, but then we'd have to find 243 to the 4th, and that's really big, and then find a fifth root. So we can do this in our heads if we put the power outside. It doesn't matter if you do the root first, then the power, or the power first, then the root. It's typically easier to do the root first because it makes the number generally get smaller, and then we raise it. The fifth root of 243 should be on your perfect sheet. It is 3, and then we are raising it to the 4th. If you need to put parentheses so you can see inside the parentheses that answer was just 3. Now we do 3 to the 4th, which we know is 81. So I didn't need a calculator, and that's the way you should have practiced those. We talked about that. All right, on the next example, we are raising a power to a power. So when we raise a power to a power, we multiply the powers together. So in your calculator, you can do 3/4 times 4/3 if you need to, or if you look at it, it's pretty easy to see that that's going to end up being 1. And so that answer just ends up being x. But use your calculator. Don't just do it wrong, just use your calculator. Now here's the one that I expect a lot of missed answers on because there were a lot missed on the quiz. Again, don't do the arithmetic in your head if you don't know how to deal with fractions. We are multiplying here with exponents, which means we need to add the exponents. You cannot add 1/6 plus 2/3 by adding the top and adding the bottom or doing all kinds of things. The only way to add them is to get a common denominator and so on. But don't worry about that. Let the calculator do that. Do not miss a problem because you don't know how to do basic arithmetic. The point of the problem is, do you know that you are supposed to add? Let the calculator add it. Just type it in. We have fraction keys It's not something that we need to be concerned with. Just let the calculator do that arithmetic. If you didn't learn how to do fractions when you were supposed to, that does not stop you from doing algebra. Okay? So we find out that it's x to the 5/6. Now, for those of you that do remember fractions pretty well, we just need to multiply the top and bottom here by 2 because that makes a 6 and a 6. So then you would have 1 plus 4, because this would now be 4, which is 5, and you have 5/6. But again, if you don't know how to add your fractions, don't let it stop you. Let the calculator help. All right, let's go to the next page. Now the latest part of the chapter that we did have to do with functions and operations with functions. So the two functions that we're dealing with are listed there at the top. Again, let this be as easy as it looks. The very first problem here has a plus sign. It says f plus g. Don't make it harder than it is. Just add them. That's it. Simply take f, which is 2x plus 5, if you look above, plus g, which is x squared minus 3x plus 2. That's it. Now just add your like terms and put them in order from largest to smallest. So there's no other x squareds, so it'll be by itself in the front. There's a 2x minus 3x, that makes minus x, and then there's a 5 plus 2, which is 7, and I'm done. There's no number in there. It says f plus g of x. That's it. The next one to the right says f minus g. So again, don't make it harder than it is. It's just f, which is 2x plus 5 minus. Now, the thing to be careful about here is you are subtracting more than one thing. You have to subtract each of the terms. So remember that you will distribute this minus to everything in there so that we're subtracting all of the terms. So we're going to get 2x plus 5 minus x squared minus a negative 3x, which makes plus 3x minus 2. Putting them in order, again, makes it minus x squared. Now you have 2x plus 3x, which is 5x, 5 minus 2, which is 3, and we're finished. I'm going to go ahead and do the problem directly below it, which is g minus f. And all you need to do is write them in the other order. So if we write g first, then minus parentheses, and write f. So that, again, we will not forget to distribute. So this does not change the beginning, and then it will be minus 2x, and then minus 5. And then simply, again, combine your like terms. So you'll have x squared minus 5x minus 3. You'll notice that your signs are all exactly the opposite from when we subtracted in the other order. If you think about it, that's how it works with numbers. Works the same here. All right, I'm going to go over here to the multiplication problem now, and we need to multiply g times f. Now, when you multiply, you've got to multiply. You've got to multiply everything in this first one times everything in the second one. So again, distribute. X squared times 2x, x squared times 5. Then you'll need to do negative 3x times 2x, negative 3x times 5, 2 times 2x, 2 times 5. So you'll have 6 things when you're done. None of it difficult, all little tiny numbers, not a big deal. So I'm going to go with x squared times 2x, which will be, maybe this equal sign, oh, I guess it's attached. Okay, so it will be 2x times x squared is 2x cubed. Then you'll have x squared times 5, which is 5x squared. Now I've done x squared times both things in the other radical, or in the other parentheses. Now I'm going to do negative 3x times both things. So negative 3x times 2x is negative 6x squared. Negative 3x times 5 minus 15x. Then I have 2 to multiply by each thing in the other. So that'll be plus 4x plus 10. Now just add your like terms and keep everything in order. Super easy. I only have one x cubed term. I have 5x squared minus 6x squared. That makes a negative x squared. Negative 15x plus 4x is minus 11x. And then I have a plus 10, and I'm finished. So nothing difficult there. Just make sure you don't skip anything. You've got to do all the parts of it. Okay, now let's do the two composition ones. This is the one that some of you did not get to very well on that activity, so you need to really listen here on how to do this. When you see this symbol, this open circle, that does not mean times, it means composition. This is the definition, and every time you see that symbol, this is what you write. Whatever's first, which in this case is G, of f of negative 2. Now, I like to write the parentheses smaller on the inside so it's more obvious that it's inside. Now, here what we're doing is we are not adding or subtracting. We're putting one function into another. Now, this says to do first negative 2 into f. So we're going to substitute into the function called f negative 2. And let me just actually drag this function down here. And I'll drag the g down here to make it a little easier while we're doing this problem. So if I substitute negative 2 into f, that means replace x with negative 2. So here we replace x with negative 2. So that'll be 2 times negative 2, which is negative 4, plus 5, which is 1. So instead of g of f of negative 2, I have g of 1, because that's what this equals. This is the output. That output now goes into g. There's not multiplying, it's in place of. So now you substitute a 1 into the places that we have x's. Well, that's super easy. 1 minus 3, which is negative 2, plus 2, which is 0. Now let's do the other direction. So the other direction says, the next problem over says to do f of g of negative 2. So again, first thing we do is rewrite it. This means f of g of negative 2. So this time we do g first. We put negative 2 into g. So be super careful here. Use your calculator, but watch your parentheses so you don't mess up your signs. Negative 2 squared is 4. Minus 3 times negative 2 is plus 6 plus 2. So that ends up being 12. So be very careful when you put this in the calculator. Anytime you substitute for x with a negative, I would use parentheses. That'll help you avoid any errors in your arithmetic. Now this says take negative 12, or take positive 12 and substitute it into f. Well, f is simply 2 times the input and add 5, so that's 24 plus 5, 29. So there's functions. Now let's do our very last thing, which is finding the inverse. And then it says, is the inverse a function? Well, we spent a lot of time on this with an activity, or you should have spent a lot of time on it, and the activity should have been pretty clear that the main important idea here is simply switch x and y. Okay, so physically, just where there's an x, put a y instead. Where there's a y, put an x. Leave the numbers where they are, leave everything. Just, it's like erasing the x and putting y instead, erase the y and put x instead. Then we simply solve this for y. So to solve for y, I need to get rid of the number that's alone so that I get the y term by itself. So on the left, I'll have x minus 2. On the right, I'll have 6y. And then I don't want 6y, I want 1y. So I'm going to divide by 6. So I get y equals x minus 2 over 6, and I'm done. It's pretty simple to find the inverse. Then it says, is the inverse a function? The answer here would be yes, because several different ways to do it, but the quickest, easiest way is we know that the original graph right here is a line, a slanted line. So it certainly will pass the horizontal line test, which means its inverse is a function. So yes, the inverse is a function. You can also graph the inverse, and basically if you can type it in and graph it, then it's got to be a function, because remember on our calculator it says things like f1 of x when you type things in. Well, that means function. That's what f means. So if you can get y by itself and the right hand side is a single thing, then it's going to be a function. Okay, that's it. Be sure you write down any questions that you have. You go back and correct things, and then you'll need to check the rest of your answers. All the answers should have been in the back. Maybe this will help you fix if you missed something else.